3, 2, 1, let's go. Alright, so where are we at? Well, it's time to attack non-homogeneous second-order linear constant coefficient differential equations. Okay, so let's get up to speed. So every homogeneous second-order linear constant coefficient differential equation we can now solve. Right, so again, here where A, B, and C are constants. Obviously, A is a non-zero constant. Now what we're going to do is allow the right-hand side to be a function, right? So now, instead of the right-hand side equaling 0, we're going to have some function, and we're going to learn how to solve that. So recall that the solution to such differential equations is going to be a summation of two things. Specifically, y sub h, which is the solution to the associated homogeneous equation, and where y sub p is any solution that we can find for this differential equation. So, to solve such equations, these ones right here, the first thing you'll always do is solve this. That gives us the y sub h. Then to finish things off, we just need to find anything that would satisfy this equation right here. Okay, so we know how to solve y sub h, right? Every homogeneous equation, you just go to its auxiliary equation, you get its roots, there are three possibilities, and that's it. That's all you got to do. Okay, so that means we need some tools to figure out how to solve for y sub p. Now, whereas solving y sub h was sort of very beautiful, right? It's just, you get your quadratic, you get your roots, and there you go. Finding y sub p is going to be a lot more subtle in a way. It's going to require a little bit more finesse. So today we're going to learn the first of two methods, the method of undetermined coefficients, and then next time we'll learn the other method. Okay. So let's start off with a problem and get a feel for how things are going to go. So here we go, we've got y double prime plus y prime minus 6y is equal to 2x. Linear, second order, constant coefficient, non-homogeneous. Okay, so first thing that you always should do, no matter what is going on, is solve the associated homogeneous. So we're going to ignore the 2x for a moment and pretend it's equal to 0. Go to our auxiliary equation, which, again, the way to form this is replace the y's with r and the derivatives with powers. Second derivative, second power. First derivative, first power. No derivative, no power. So r of the 0 is 1. And, oh boy, somebody was nice. This factors into two distinct pieces, so we have two distinct real roots. So the homogeneous is easily formed by looking at e to the roots. So e to the 2x and e to the negative 3x. Scale them together, add them up. Those are linearly independent, so scaling and adding them does give us a new answer, and that's it. Okay, so we've solved the associated homogeneous. So now what we need to do is figure out a particular solution. Okay. So how can we possibly do it? Well, we looked at one way back when we first started talking about this material. And basically what we did is, well, if you look at this equation and you read it, right, find me a function whose second derivative plus its first derivative minus 6 times itself gives me 2x. 2x is a polynomial. Specifically, it's a first-order polynomial. The highest degree, the highest power that appears, is 1. So very similar to the order of a differential equation, by the way. And as we've already noted, there's a lot of overlap between the theory of polynomials and the theory of differential equations. So, because the left-hand side is derivatives of functions added and scaled together, right, it's pretty reasonable to guess that y should be a polynomial, right? Because we want to take derivatives and add them up and make that equal a polynomial, so guessing a polynomial is completely and utterly reasonable. But what should we guess? Well, the right-hand side, although it doesn't look it, is a first-order polynomial, which means that not only is it ax, but it's ax plus b. Right? The b on the right-hand side is equal to 0, so it doesn't show up when we write the equation, but it's there whether or not we see it. So it stands to reason that we should guess something that looks like that form, because we're going to take derivatives and add it all up, and that it seems pretty reasonable that this should work. Okay, so plug that into the DE, and now we have coefficients that are currently undetermined, hence the name. Okay, so now we've got two polynomials equal to each other. On the left-hand side, we have 2x, and on the right-hand side, we have negative 6ax plus 6 minus a minus 6b. Okay, the only way two polynomials could ever equal each other is if their coefficients are the same. Right. If your polynomials have different coefficients, they do not equal each other all the time. They might overlap, but they don't equal each other all the time. This is saying that they are literally equal. The only way that could happen is if the undetermined coefficients matched up. So negative 6a equals 2, and a minus 6b equals 0. This is not the hardest thing in the world to solve. A is negative 1/3, that forces b to be negative 1/8, and so the particular solution, negative 1/3 x minus 1/18. Right, and now note here, the plus b term needed to be included, right? There was an actual value for the b. If you only plugged in ax, which is exactly what the right-hand side looks like, you're quickly going to find that you're going to be in trouble. Right, that shouldn't be too surprising, because note, if you just guessed ax, you'll still have the negative 6ax showing up, but now you'll also have a plus a that you can't match to anything appropriately, right? The plus a would tell you a is 0, but then that would tell you 0 is equal to 2, and yeah, it doesn't work. So the plus b was necessary. Okay, and it's worth stressing that, because as we're going to see, we got to be, when we're making these guesses, we're going to have to be very careful about what we do. But anyway, we can now tell you what the general solution is. So we solved the homogeneous, c1 e to the 2x plus c2 e to the negative 3x, and now we've found a particular solution. We found something that worked. Negative 1/3 x minus 1/18. It's rigged to work. Okay. So this seems to indicate, this example and then the one we saw much earlier, that all we have to do is just make a pretty solid guess, have some unknown constants, plug it in, and solve. Can't be that easy, can it? Alright. So here we go, y double prime minus y prime. So your first reaction to this one is, well, the right-hand side's the same. So before we even get into it, you're probably going to go ahead and go, okay, ax plus b, plug it in, that should work. Okay. Now, this would be a good time to pause and give that a go and discover that it's not going to work. But hopefully you quickly see that you're going to be in trouble. Ax plus b, its second derivative is 0. And its first derivative is a constant. So on the left-hand side, we only have a constant. And on the right-hand side, well, we've got a polynomial. So the thing to guess, ax plus b, completely will not work. Okay, but why? All right, well, let's look at the associated homogeneous equation. Okay, so the auxiliary equation for the associated homogeneous equation is 0 is equal to r squared minus r. So my homogeneous solution, the general solution there, is c1 plus c2 e to the x. Okay. And like I just noted and said, the natural guess of ax plus b falls apart because we get 2x is equal to a constant. Not good. And that should be a minus a, not a plus a. It never ends. Just when you think you caught all the typos, they just keep coming. It's never, you know, I feel like I had a good string in the beginning where I didn't have any videos that had any mistakes, and just now it's like everyone's got like, in your head it makes complete sense, but when you write it down, it's totally wrong. Trust me, I feel you. If you've ever been on an exam and you left it going, I did perfect, then you get back and you get like a 63 out of 100. I can't tell you how many exams I took in college that were exactly like that. The worst, though, are the ones where you're like, I did terrible, you get back and it's a 93, and you're like, what? Come on, I didn't do that good. But anyway, alright. Now, why did this happen? Why did the guess fall apart? Well, you can see exactly why. Our guess has a plus constant term. there is a plus constant term in the solution of the homogeneous, right? A constant, when plugged in, is going to give you 0, right? That's what the homogeneous solution means. Y prime minus y prime equals 0. It satisfies that. Plugging a constant in will introduce a 0, so it will remove that part from the guess. And that's exactly what we see here. B does not show up. So when we make a guess, we have to check it with our homogeneous. You always need to do this. There is an overlap between them. This guess is going to be bad because the overlap is going to get killed, right? Because it is part of the homogeneous, plugging it into the DE is going to zero it out. And we don't want that because we want to line up with what's on the left-hand side. Okay. So this is representing basically the main thing that goes wrong with the method of undetermined coefficients, of going ahead and saying, let me guess something that looks like the right-hand side, plug it in, and check the coefficients. You need to make sure that your guess does not have any overlap with y sub h. So what's the secret? What's the move? Okay. Well, let's look at this again. Y double prime minus y prime equals 2x. So I want something whose derivatives, when I add it up, gives me a polynomial. So I still want to guess a polynomial. Right, I'm not going to all of a sudden do plus cosine. That's probably not going to work. So I need a polynomial that does a little bit better. All right. So how about we multiply it by x? That gives me ax squared plus bx. That's a polynomial. No longer does it have an overlap with the homogeneous. And plugging it in, hey, check it out. We solve for a and we solve for b. Excellent. So now, worth noting that maybe your first reaction was, well, let's extend the order, right? Instead of ax plus b, do ax squared plus bx plus c. Now, that's a good idea. That's a slick idea, even. But the problem is that plus c we already know is not going to help us because a constant gets killed. So this multiply by x trick is doing exactly what you think you should do, increasing the order of the polynomial. But if you keep the plus c, well, the plus c will just vanish and it won't matter. So really, the x squared and the x term are what matters. But anyway, after plugging them in, we solve for it. We've now solved a particular solution. Negative x squared minus 2x. I have the general solution. I have a particular solution. Bing, bang, boom, done. All right. Probably gets worse. And oh boy, it gets worse. So, all right. Here's another one to consider. Y double prime minus 2y. That should be y prime. Ooh, the hack fraudery today is extreme. Yeah. And I mean, from context, obviously I meant y prime, but you know, should probably type it correctly. Alright, anyway, so before we even go guns blazing into this, let's think about what we would probably guess. Right, this would be a good time to pause the video and give it a go. The right-hand side is e to the t. The left-hand side is derivatives being added up, and I want them to equal e to the t, so I'd probably guess something times e to the t, like a e to the t. Seems like a pretty reasonable guess. Okay. Now, you can, of course, plug that in and try, and guess what? It's not going to work, because the auxiliary equation is this. That means the homogeneous solution is this, and hey, a scalar multiple of e to the t will not work. That overlaps with the homogeneous. So for polynomials, the trick we saw there was, hey, slap it with the independent variable. And, oh yeah, look at that, that's another overlap. So, e to the at, which would be a pretty reasonable guess, is bad. And the trick we saw with polynomials, multiply by the independent variable, will also be a bad guess. So what do? All right, do we have to get really creative here? No. Multiply by another t. So basically, just keep multiplying by t until it works. And I'm laughing because it seems very silly, but this is literally what you do, and it's literally going to work. So let's give it a go. Taking the derivatives, plugging them in. Here we go. I've already done the work. And oh, look, ta-da! A is a half, and therefore we're done. So So it's not too bad. So when you're doing undetermined coefficients, the basic idea of, all right, let's make a guess based on what the right-hand side is, and then compare that guess with what the homogeneous looks like, and then make modifications to make it work, basically. This is the method. Right, it's not, turn the crank. There's no formula. It's a little bit of finesse. Your textbook has a little table where they're like, if the right hand side's this, then you guess that, and then if the homogeneous is this, then you do that. So there's some decision trees that are available to you. I'm more of a fan of not memorizing all that stuff. It's just when it comes to polynomials, exponentials, and trig, guess something that looks like it and plug it in, and see how it goes. All right. So that being said, we've seen polynomials, we've seen exponentials, so let's now attack trig. Okay, so let's make it a little bit more fun and do an initial value problem. Alright, so again, perfect time to pause the video and give it a go. So you can go ahead and just do that. While that's going on, I'm going to take a DDP break, take some Diet Dr. Pepper. Alright. Alright, now let's give this a go. Okay. So again, the first thing you should do is always solve the homogeneous. Always, 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 always do homogeneous first. I don't care if you've got some crazy idea for what the right-hand side should be for the particular solution. Always go to homogeneous. Just have it on hand. You need it to get the general solution, so just do it first. And as we discussed, knowing that is going to help us dictate what the particular solution's form should be. Okay, so the auxiliary equation here is r squared plus r. So we get two roots, constant and constant times e to the negative t. Well, that's good news for our particular solution because there's no overlap with what the right-hand side looks like. So our guess here should be pretty easy to see, but we're going to have to be a little bit careful. Because your initial reaction is, well, the right-hand side's cosine, so let's guess, right, scalar multiple of cosine. That's not going to work, right? Why is that not going to work? Well, its derivative is negative a sine of t. I don't have any sines on the right-hand side. So if I guess this on its own and plug that in, well, a sine term is going to show up that I have to deal with, but I have no way of matching it on the right-hand side. So this reveals to us what we're going to have to do with trig. If your right-hand side is trigonometric, and by trig here I specifically mean sine and cosine only, we're going to have to guess both terms, because their derivatives cycle through themselves. So if the right-hand side is cosine, you obviously will guess something else like cosine, but we also need to include sine, because cosine's derivatives involve sine. Makes sense. And although it's not happening here, if there is an overlap, the multiply by t trick will also work. And though, as you imagine, very quickly these sprawl out of control. So if you've got a particularly nasty one, it's not a good time. But anyway, all right. So that's the guess. So let's go ahead and do it. Taking two derivatives, adding them up. Okay. So not only do we have a cosine term we can work with, there is a sine term that we can work with. Okay, so specifically we know that b minus a needs to be equal to 2, and a minus b needs to be 0. So a is negative 1, and b is 1. So the particular solution involves not only cosine, but also sine showed up. Right, and at first glance that might seem a little weird, right, because the right-hand side only has cosine, but again, the derivative of cosine is sine, and we've got the derivative on the left-hand side, so sine showing up to the party isn't too surprising. Alright, so we've got the general solution, right? We solved the homogeneous. Right, note, nothing to do with the right-hand side involving cosine. That's where this negative cosine t, sine t shows up. And again, note, no constants on that. Just anything that works. Alright. And I'm done, right? I look at the slide count. There's still another slide. What's going on? Oh, yeah, that's right. Add initial conditions. Ooh, yeah. So the worst thing you could do is do a bunch of work and then just be, hey, I'm done. And then not have actually answered the question. All right, so we got to plug in the initial conditions to help us out here. Now, the thing to remember with non-homogeneous is that you need to plug the initial conditions in after you've solved both y sub h and y sub p. You need both of them, right? Because that's what y is equal to. We're told information about y. We're not told information about y sub h or y sub p. We're told information about y. Okay. So to solve the C1 and the C2 that appear in the full-out solution, not just the homogeneous. Rookie mistake. Plug this only into the homogeneous. Do not do that. Okay. Alright. Now I've got information about y and its derivative, so I need to compute its derivative. There we go. And now we plug in the initial information. Alright, and from here we see that C sub 1 and C sub 2 are equal, and they're both equal to 1. And so the unique solution to this differential equation is 1 plus e to the negative t minus cosine t plus sine of t. And that's it. There we go. Alright, so we've now gotten a pretty good flavor of the method of undetermined coefficients for solving non-homogeneous, linear, second-order, constant coefficient differential equations. But as we noted, it's not exactly the best method. It's very much just make guesses and hope they work and be smart about your guesses. But there's going to be equations that's just not going to work, is it? Wonder if that's what we're going to learn next time. See you then.